Hello, everyone. This is Michael E. Yeaman with another Geology of Sculpting Stone. Today, we're going to talk about North Cascades Dunite, which is composed almost entirely of the mineral olivine. So, why should you care about the geology of your stone? Well, stone sculpture is an art form that dates back to the very beginning of history, and stone is unique among art. Knowing more about the geology of your stone will allow you as a stone sculptor to specifically understand the various stone types and understand their compelling history, which is of interest both for you as a sculptor and your viewer alike. You can marvel at the various colors, textures, and composition as you work it. You can consider how your sculpture's chosen artistic form relates to the science of the stone. And finally, you can weave into your final artwork the geologic story, which enhances the value and the interest of your work for both yourself and potential buyers. As usual, we have an outline of three components. We talk about the stone defined, its general description, specimens, and specific occurrences. We'll spend quite a bit of time talking about the geology of the stone, the age and description, its formation environment, where it was located in the world when it was formed, and are there any modern analogs? And then finally, we'll take a look at some art and architecture made from the stone. Let's begin with the general description and physical and chemical properties and historic use of dunite. Dunite is what's known as an ultramafic rock. That is a rock that contains a large amount of iron and magnesium, and it's mostly composed of the mineral olivine. It may, however, contain minor amounts of chromite, pyroxene, spinel, and magnetite. We'll discuss more about that later. Dunite itself is a dense and hard mineral, specific gravity of 3 and Mohs hardness of 6.5 to 7, which makes it fairly hard, particularly compared to something like common granite. It's usually coarse grained, green in color, but notable because it quickly weathers to an orange-red rind, particularly the red colors, which are tied to the iron in the stone. Dunite is found in the North Cascades, where it makes up the entire Twin Sisters Mountain area, which is just south of Mount Baker. It's an outcrop that's about 16 kilometers long and about 5.5 kilometers wide, which makes it one of the largest outcrops of dunite in the world. In fact, I believe it is the largest outcrop of dunite in the world. It's been mined since the early 20th century, but it's never been a large producer of stone, less than 100,000 tons per year. Its specialty use as a slag conditioner, refractory, or foundry sand, and as a fertilizer makes it particularly targeted to the industrial sector. And in addition, its physical properties are useful as abrasives and other types of characteristics make it particularly useful for heavy industry. Its gem characteristic, olivine's gem characteristic, is known as peridot, and its particular popular crystalline gem. It's used in jewelry, and it makes beautiful green gemstones. It's interesting that I was reading that an intriguing future use for olivine and affiliated dunite would be as a way to remove carbon dioxide from the atmosphere to slow down global warming, part of the CO2 extraction concepts for the Earth's atmosphere. On the right, we have a description or a clarification of the chemical composition of dunite. You can see that there's the magnesium and iron tied in with silicon oxide, which gives it that bonding element with minor amounts of some of the other minerals we mentioned below, pyroxene, chromite, spinel, magnetite. But again, it's almost entirely made of the mineral olivine, which is the primary magnesium iron formula we see above. Now, if we take a look at the global distribution of dunite, you can see here on our world map, Twin Sisters there in Washington State. There are several other outcrops throughout the world, although, again, dunite is a rather unusual mineral. We'll describe a little bit more about that later, about why that's the case. I want to point out one area here in New Zealand down to the south. So here what we have is a place called Dun Mountain. It's also a very large outcrop of dunite, and it is the type locale where the word dun gives dunite its name. So in these Geology of Sculpting Stone presentations, I always show both macro and micro pictures. Here are some pictures of Dunite in the Twin Sisters area, and you can see that little vegetation actually grows on the stone itself. That's because of the intense iron and magnesium in the rock itself. The picture on the left is an exposed natural occurrence here in the Twin Sisters Dunite area, and on the right is a fresh outcrop from the Olivine Corporation's quarry, the only active quarry in the Twin Sisters mining Dunite. If we take a look at thin section specimens, as with previous presentations, I've talked about how these thin sections are made, very thin slices of the rock, and then put underneath microscopes, and different types of light are reflected through them. And because of that, you can actually gain a good sense of the mineral composition just based on the thin section analysis with the light shining through it. Here at about 100 magnification, we have a comparison of a number of different thin section slides from the Dun Mountain. If you recall, that's the location where Dunite has gotten its name from New Zealand. And you can see many different styles of Dunite and the mineral characteristics of them brought out here. Some of the olivine being particularly notable, that on the upper right, that diagonal looking line being the strong element of olivine containing that. Oftentimes in these thin sections, when you see black spots, it's especially if you know it's an ultramafic rock, it's oftentimes magnetite. So a lot of the black spots in these thin sections with the light shining through them are magnetite. The crystal face interfaces are interesting. You can see a difference, for example, between the lower left slide with these nice angular lines here. I'll mark a couple of them. Here's one, and then here's another. And oftentimes the 120-degree angles are a giveaway of different types of crystalline formations, feldspar, or in this case, olivine crystal development. Here on the right, the lower right, you can see that the crystals don't have this nice sharp outlook and angled line. And in fact, they almost look a bit smeared. And as the slide's implying, this is olivine that's gone into some deformation, and the banding within it and the quote unquote smearing of the crystal faces are a sign of the olivine being strained by some sort of tectonic pressure environment. The amount of olivine, the magnesium, pyroxene, spinel, some of the other trace minerals in the Dunite in thin sections make them extremely colorful. Actually makes the job of a mineralogist quite pleasant when you have this attractive of thin sections. And also we decided, as you know, in all these presentations to talk about specific occurrences. Here is a picture of the Twin Sisters, the above right area with the north and south Twin Sisters here looking to the south. And in the lower left, we have a picture aerial view of Mount Baker and the Twin Sisters to the south-southwest of there. Oftentimes snow-covered during, well, pretty much all year round. The town of Concrete is located right down here at the bottom, give you a sense of location. The Twin Sisters are a beautiful twin-peaked set of mountains, quite visible from the coast as you look back to the east. So in this slide of specific occurrences, let's take a look at a little bit of the surface geology. And so what we have here is a surface geologic map of the Pacific Northwest area, specifically centered around the town of Bellingham. Here are the San Juan Islands off here to the west. And off to the east, we have the high Cascades, specifically ending somewhere just this side of the Continental Divide, or at least the Cascade Divide. So what we have on this geologic map in color is different rock types, each given its own specific color and two-letter designation. And what I wanted to dive in on is this one right here in the middle. Now you can see this is a unique color type and it's labeled TS. Well, guess what? There is our Twin Sisters Dunite. So as we talked about before, the Twin Sisters Dunite is a unique geologic formation made up almost entirely of the mineral Dunite, and which is made of itself of olivine. And it's a unique formation, again, about 25 by 15 kilometers wide, and it stands out here in the geologic map of the northwest area around Bellingham as a very distinct block. And I want to point out a couple of things here. You can see that there's a couple of dark lines that that go down the west side of the Twin Sisters Dunite area. And you can see that those lines run oftentimes quite a long ways, all the way from south to north, and that there's several of them. And one in particular is labeled the Devil's Mountain Fault, a very important fault for us here in the Pacific Northwest. But these black lines are faults, offsets in the individual rock types that make up the geology of the Pacific Northwest. And there's a very prominent one that's featured just west of the Twin Sisters Dunite. It disappears below some other later stone and into other things to the north, but it is a major fault itself that runs right along the west side of the Twin Sisters Dunite. Now, if we take a look at something that is a geologic cross-section labeled B to B prime, all this really is drawing a line across the surface geology and looking down below the surface and thinking about what exists below the surface as a cross-section. So here on the west, here where B is, we have Orcas Island, made up of a couple of different formations like the Orcas Chert and a few other groups, the East Sound group. Crosses over to Lumi, up in the Chuckanut, the Sandstone Mountains of Chuckanut. And then finally here we have right in our middle again, the Twin Sisters, the TS. And you can see here are these vertical lines right next to TS, and those are the faults, the very significant faults that bound the west side of the Twin Sisters, the TS shown in the map. And the reason that they're so important about our specific currents of the Twin Sisters, it's those faults and the movement upward of material along those faults that expose the Twin Sisters, the Dunite and the olivine of the Twin Sisters, which normally would be very deep, form very deep. We'll talk a little bit more about that in a minute. Below the surface, it's those big faults that move the Twin Sisters all the way back up to near the surface where it is today. It's that unusual, great deep faulting that makes our Twin Sisters quite unique in the world's largest outcropping of Dunite. So as we go into the age and geologic description of Dunite, let's talk a little bit about background for geology. I'm going over something probably most of you already know. Three basic rock types: sedimentary, igneous, and metamorphic. The rock cycle here, this area over to the right where it's a simplified diagram, is a classic diagram. And if there's any one single geologic diagram that allows you to understand how different rocks are all connected, this is probably a great one. It begins with the idea of rocks being possibly deposited or lithified in sedimentary rocks, being buried and warmed up to create metamorphic rocks, maybe being buried deep enough that they actually melt and form a magma. Then as the magma cools, it forms igneous rocks, which then perhaps even come up to the surface as volcanoes, get weathered by rain and other events, get washed down, and start the whole cycle again. So the rock cycle diagram is a very useful way to think about the relationship between sedimentary, igneous, and metamorphic rock. So just to remind us, Dunite is an igneous rock, and it's actually created all the way down at near the Earth's upper mantle. So that's the zone where many times things are beginning to melt right down in here. So let's talk a little bit more about that. Well, we can begin by looking specifically at how Dunite fits within the spectrum of other types of rock. And this is a complex diagram on the right, but we can just focus on the pieces that we want. As I mentioned, Dunite is an ultramafic. It's one of the most ultramafic rocks. The Twin Sisters Dunite, the ones in Washington State, formed way back in the Triassic to Middle Jurassic, about 240 plus to 180 million years ago. And the emplacement or the forcing in of the Twin Sisters Dunite against North America is thought to have happened that blob coming up on the faults that we just looked at the couple of previous maps we think probably happened sometime in the late Cretaceous period after it was formed, in by timing about 165 million years ago. Now, in this schema on the right here of this simplified scheme for igneous rock identification, there's a lot of information here, but what I want us to look at and focus on is a diagram that we've used in other geology of sculpting stone presentations, and that's this diagram down here that breaks out different compositions of the core minerals of most igneous rocks: potassium feldspar, quartz, plagioclase feldspar, biotite, the black type of being called muscovite, some complex minerals called amphiboles, pyroxenes. But here we are, way over on the far right, the mineral olivine in green. And you can see that here I've mapped that and tied it all the way up to the top here in the upper diagram, where I've linked the word Dunite, which is specific type of this ultramafic rock. And you can see that in this Dunite area that it is a subcategory of this ultramafic material called peridotite. But the most important thing to point out is that it is made almost exclusively of olivine, as you can see from the lower diagram, and it oftentimes is coarse in texture, doesn't contain a lot of vesicles because it was formed quite deep under a lot of pressure, and is the extreme mineral magnesium iron mineral element of igneous rocks. So let's also talk a little bit about the visual description of its age and geology. As it occurs in nature, at least in Washington State, we see the Twin Sisters, because of its high iron content, rapidly weathers to this reddish orange kind of color. It's very noticeable. In fact, it's a distinctive field characteristic because very few rocks will weather to the bright orangey reddish color of Dunite. Cobbles are found in other formations as these pieces of Dunite have broken off and been included in other stones, say volcanics or other things that are formed with time. Some of the fresh faces of the Twin Sisters Dunite, by a fresh face, I just mean somebody that's been recently broken away from a weathered outcrop. You can oftentimes see the fibrous green olivine and black spots, the chromite minerals, and also when, in certain cases, these Dunite specimens will contain fractures, and those fractures will fill in with 100% olivine, which will crystallize more slowly. And as it cools slowly, these crystals become bigger. And so when you polish them, here now on the lower right, I've taken a specimen of Dunite I made into a sculpture a long time ago, polished it up, and you can see the finer grained greenish colors Dunite above and below. And then in the middle, in this vein here, and in this picture also on the left, you can see more coarser grained, larger grain material that is also Dunite, or could even be 100% pure olivine. And these crystals are coarse enough, you might also think that they've almost reached the level and size of a coarse crystal to be considered the gemstone peridot. So as we step back and take a look at how Dunite actually forms, let's begin with a simplified map of the structure of the Earth. And here I've done a standard pie diagram, oftentimes used in geology as a cross-section of the overall Earth, giving you a view all the way from the very top where the continents and oceanic crust are located, all the way down to the core. There is a lot of science in this diagram, but we're going to focus on an area called the mantle, which is an area about 5+ miles on down below the surface of the Earth. And it's where a lot of the action for the formation of certain igneous minerals occurs. In here, a lot of the minerals, based on density and other reasons, are ultramafic silicates. All that means it's igneous rock that has particularly high concentrations of iron and magnesium. It's where we see Dunite, and of course, its major component olivine. And there's a lot of that mineral, Dunite / Olivine, in the mantle, particularly the upper mantle. Again, giving you a sense that our mineral is kind of unusual because it's normally found much, much deeper in the earth, not near the surface. So one of the questions is, how did our Dunite get to all the way up to the surface of the earth, and why in Washington State? Well, to explain that, we have to go back to our old friend plate tectonics. And this diagram has appeared in many of my Geology of Sculpting Stone presentations, and it has the standard elements of plate tectonics. We're not going to spend a lot of time on this. All we really want to point out is that one key element of plate tectonics, when these pieces of plates slide and bump against each other, when an oceanic plate bumps up against a continental plate, you get oceanic crust and continental crust, and oftentimes when they compact or collide, the oceanic crust will dive down beneath the continental crust and produce a subducting plate, which will begin to reach this hotter lower area. It's an area of the upper mantle, which will begin to form some of the minerals we just discussed, the Dunite, Olivine, and some of the other ferromagnesium minerals. Also, I want to point out this area a little bit to the east, just off here, where a spreading ridge can develop. Now, it's an area where the molten material from the upper mantle is allowed to well up and spread away from the ridge in both directions. There's a lot of plate tectonics going on here, and it could be a whole presentation itself, but we won't be doing that today. Let me just point out, however, that we've got a couple of zones where we've got this upper mantle material beginning to get to the surface, or beginning to get formed and moved around on the Earth's surface. One is where the plates are diving down, as we mentioned, the oceanic crust diving down beneath the continental crust, and the other location being where it's upwelling near one of these mid-ocean ridges and spreading both to the both sides of the ridge as a thin plate of new crust. So let's talk a little bit more about this. And let's zoom in on particularly these two areas we just spoke about. One where the subductive plate is getting deep down near the upper mantle surface, and the other a zoom in around what's happening in the mid-ocean ridges area. And specifically, I want to talk a little bit about the mid-ocean ridge area where the spreading center, the quote-unquote spreading center, begins to occur. When the mantle convection begins to pump in liquid material from the upper mantle and forms as a magma chamber, a body of liquid, hot liquid, oftentimes ferromagnesium rich olivine type material, it forms a body that begins to move up into the continental crust. And as it moves up into the continental crust, in certain places, these mid-Atlantic ridge places, it begins to break through and cool and flow on both sides as it moves away from this spreading mid-Atlantic ridge. Oftentimes they're called a spreading center. Now, it makes a very distinctive set of stones, of minerals, as it comes into the shallow crust, cools and spreads away from the spreading center. And that set of minerals is referred to as an ophiolite sequence. I'm going to highlight it again, ophiolite sequence. So the ophiolite sequence of layered rock is what what occurs near one of these plate tectonic centers of spreading. And because they move away slowly as this material is injected, they're oftentimes referred to as a plate tectonic conveyor belt. That being that you get the material to form, it cools, more material is injected, and both sides move away. So you get a constant development of this layered material all the way from the melt material down below here in the upper mantle up through the magma chamber to the surface. And as it cools, based on the temperature, the pressures involved, it layers into different types of rock. This layered peridotite, which we saw before in that previous diagram, includes Dunite. Above it is gabbro, a darker ferromagnesium mineral related to granites. sheet dikes, these are just vertical elements of igneous rock that form and cool in a sheet type way, oftentimes with vertical components. And then finally, at the very top, right at the oceanic water magma chamber liquid interface, you get what's called our pelobasalts. And pelobasalts are strictly lava that's been erupted into an aqueous or water environment. And as it cools, the natural way for it to cool quickly are to form large pillows. So this ophiolite sequence we just talked about, which occurs at a mid ridge or mid-oceanic spreading center, has many different components, but the most important one for us is what happens right down here at the bottom, this layered peridotite. And in that layered peridotite, you will see near the bottom of it, oftentimes the mineral Dunite or 100% olivine. Now, as we mentioned, besides the ophiolite sequence, we also have some things occurring as a subducting plate. Oftentimes in our case, we're talking about the oceanic crust, begins to dive down beneath perhaps a more North American type continental crust. And as the subducting plate, this oceanic subducting plate begins to dive down beneath this North American, more continental plate, on top of it, on top of the subducting plate here, is oftentimes one of these ophiolitic sequences. Now, that's just that pile of rock we are looking at. And as you recall, it has some little bit of sediment on top. There's our pelobasalts, and then some vertical dikes. We have our gabbros. And then here at the very bottom, here we are. Here's our Dunite forming at the bottom of our ophiolite sequence. And then below here, we have even more 100% ultramafics down below here, if they're preserved at all. But most importantly, this ophiolite sequence sits on top of this subducting plate, and the plate itself begins to dive down underneath the continental crust. Oftentimes, this ophiolite sequence is scraped off as it's subducting. That component is peeled off, basically a combination of friction with the North American craton, in our specific case, the continental material. And this ophiolite sequence is oftentimes scraped off and abducted, meaning that it's put on the bottom of the continental plate that it's diving down below. So this abducted or scraped off material contains pieces of this ophiolite sequence. And guess what? In that ophiolite sequence, like we just talked about, were chunks of this Dunite. All right, so how does this all tie to our stone that we sculpt here in the Pacific Northwest called Dunite? Well, it began when this scraping or abduction occurred, and that was about 75 million years ago. So here we have a slide that talks about the formation environment and processes by how our Dunite formed. Now, as I mentioned, a key element of getting Dunite scraped off from an ophiolite sequence involves a subducting plate underneath a continental landmass in our case. So here is a picture of what North America looked like on the West Coast 75 million years ago. And here we have one of our subducting plates. It is, at the time, this fragment's called the Kula plate, and it's diving underneath this big mass of granitic material, continental material, that's North America, forming a mountain range and volcanoes, the Chilliwack group of ancient volcanoes from 75 million years ago. But here we see now, here in the middle of this little diagram here, this little cross section, some of this ophiolite sequence being scraped off or abducted in underneath the North American plate. Now, this fragment, oftentimes referred to as being part of the Farallon plate fragment, formed a number of different things, including Vancouver Island and several other island pieces up along British Columbia. It had an east-west trending set of tectonic elements which can be described as being part of the descending oceanic plate. That's the Kula plate elements that's diving underneath of North America, and part of this descending plate created what's called a melange belt, and we won't go into this tricky French term that talks about basically a bunch of mixed up sediment, but it formed in parts of southwest Washington, and included in this melange belt was the Twin Sisters Dunite. So here it is. It's part of this ophiolite sequence sitting on top of the Kula plate, and as it's diving down below here, it gets scraped off and abducted onto the bottom of the North American plate, and part of it is our lovely greenish, weathering to orangey color Twin Sisters Dunite. Here's a picture, by the way, of what the world looked like when this was occurring about 94 million years ago in a period of time called the Late Cretaceous. And what I've done here is I've shown up in the upper left this melange belt subduction. Remember, that's the little piece that's being scraped off in North America that includes our Dunite. And here its location. You can make out most of the continents are somewhat recognizable. There was a big seaway in North America at the time. But the general overall outline is North America is pretty recognizable. South America, Africa, the Atlantic wasn't open quite as far as it was. The spreading center for us is way over here, the Pacific Ocean. There's the spreading center running right down the middle of the Atlantic. All fun things about plate tectonics. Someday I need to do just a plate tectonics talk. But we're focusing on the geology of our sculpting stones. So here, we're just interested to know that you can tell people when you work on Dunite that it was attached to North America by one of these subducting plates about 94 million years ago as it scraped off the Dunite on its way diving underneath North America. Now, in this Geology of Sculpting Stone series of lectures, I always ask, are there any modern day analogs where a stone like the stone we were talking about today, it's Dunite, might be forming today? Well, maybe it's forming right now under Washington State, even as we speak, because frankly, the processes that created the Dunite 94 million years ago, or actually the Dunite itself as a stone was created much earlier, but scraped off 94 million years ago, those same processes are occurring today. We have a different set of ridges, spreading ridges. Now we have something called the Juan de Fuca Ridge, and that's spreading to the east and west. But it now is diving underneath the coast of Washington. It has a magma chamber that is the source of that rich iron, magnesium rich ultramafic rock that's coming into the San de Fuca Ridge. And it's spreading to, in this case, to the east. And as it dives underneath Washington State, there's material that's being scraped off. So could some of that material that's being scraped off include Dunite? Well, it's quite possible. It is indeed quite possible. But one particular thing about our modern analog here is that we need a way in which the Dunite itself can actually get to the surface. And as we saw in that earlier geologic slide, it really was the combination of all the faulting that occurred in the period when the Dunite was being scraped off, that faulting that brought something that normally would dive deep within the mantle or upper mantle and be melted again. It was actually faulted all the way back up to the surface. So where we see it now, just southwest of Mount Baker, is an unusual circumstance that brought that Dunite all the way back up to the surface, which normally would have stayed abducted or attached to the bottom of the continent, and we might never see it. That's why Dunite is a rather unusual stone to see near the surface. Could that happen again here as a modern analog? Well, if the faulting's right, some of the strike slip faults we have, like San Andreas, and some of the big faults that still make the Northwest very seismically active, is certainly part of the puzzle, but it would require that type of activity to bring the potentially abducting Dunite, which is happening underneath Washington State now, back to the surface. Here's some of the big, beautiful mountains in our area. Maybe one day one of those will be eroded off and be shown to have Dunite underneath it. Well, let's close out with a discussion of the art and architecture that's created from Dunite. Well, the reason that's particularly important for the Northwest Stone Sculptors Association is because it's a massive outcrop, easy to access in the sense that it has a large active quarry, and that over the years, we've collected large amounts of Dunite from stream beds running off the Twin Sisters. And then a number of years ago, some of the more industrious members of our association got together with the owners of the Dunite quarry there on the side of Twin Sisters and actually convinced them to work with us as an association and have us access the quarry directly to take away some stone to be sculpted. And over the years, that relationship has grown to being quite special. And as many of you know, every year now we have an auction, charity auction for a line item so that many members can head up there with their pickups and load up on Dunite and use it to sculpt some of the amazing pieces our association has made over the years. Individuals like Pat Barton, Ken Barnes, and even yours truly have created pieces from Dunite. You can see here, just in these three pieces, the remarkable variations in color and texture, and where, for example, Ken might leave some of the rind on his to form a very distinct character, and Pat might give his Dunite a multicolored greenish organic element. And here I've done something quite geometric where you can actually pick out some of the different characteristics of the weathering Dunite, including some of these little black chromite dots down here in the lower portion of that sculpture. Anyway, many of us here in the Northwest Stone Sculptors Association have created many different types of sculptures from Dunite, from big to small. Architecture-wise, Dunite's a little bit trickier. It's never been actively quarried as a building stone, to my knowledge. Right now, the active quarry uses dynamite to extract most of the material, or large front-end loaders, which fractures the Dunite quite a bit. And because it is almost entirely olivine, it has a tendency to fracture rather readily on one or more planes. Because it's also very coarse crystalline, it does have a tendency to break up fairly easily. So it's difficult to find really large pieces of unfractured Dunite for architecture. But some of the industrious members, including Dean at Princess Jade in the past, have done innovative things, including countertops. There's a number of wonderful Dunite benches that you can still find at various shops around the Northwest and Bellingham area, and signage and things. It makes really a lovely stone. It's coarse and crystalline, as we mentioned, so it has wonderful optical properties. And architecture, although as a building stone it's rather limited, it almost produces gem grade quality stones for countertops or other purposes that you might have in mind. And by the way, you can see here in this bench that Dean created this little coarse-grained vein of olivine, probably peridot in gem grade quality. So in conclusion, what can we say about Dunite here in Washington State? Well, I think Dunite is one of the most special stones the Northwest Stone Sculptors Association sculpts because it is unique. And particularly in North America, it is one of the few outcrops we can get to in North America, and it is the world's largest single outcrop of Dunite, again, almost 100% pure olivine in the world. It's a stone that can be worked both by hand tools and by diamond tools, and although it's heavy and dense, it actually works and polishes as a much softer stone. Many of us have found that as we've worked it, that it is remarkably pliable and can be shaped both into strong linear forms and organic forms, figurative and abstract. So it's a stone that has a lot of cross functionality. It has wonderful properties if you keep rind on it, the reddish orangish rind of weathered Dunite, the iron that contains in there. And as you polish deeper in the stone, you pick up more and more of the deep greens, and then occasionally you find some lovely peridot gem quality inclusions in the stone. So in the world of special stones, it doesn't get much more special than Dunite in Washington State. And if you create Dunite sculptures, you should certainly know a little bit about its geologic history, because it is a wonderfully unique stone, very unique in almost the entire world. Well, this is Michael E. Yeaman closing out with another Geology of Sculpting Stones. We will see you next time.